Well, welcome back to part 3 of upgrading my mini lathe. In the last episode we were able to complete the gib strips, and today what we're going to do is fit them to the saddle. So that will involve opening up the clearance holes, drilling and counterboring for socket head cap screws. In the meantime, I ordered some 2BA socket head cap screws for the holding down bolts, and I'd also like to try and machine the dovetails in the cross slide. If we can do that, then that will be good progress for today. Now that we've completed the operations in the planer, it's time to open out the 2BA holes to a clearance size, and after that we'll do the counterboring. So to start with, I'm going to use the minimum possible clearance hole. We can always open them up if we need to, but if I've measured my holes accurately, then we should be able to use the smallest clearance recommended, and then we can always open up if necessary. Okay, we're ready now for drilling and counterboring, and just double checking that I've got the gib the right way up. So that sits on the saddle, and it's this side needs to be counterbored. So I've set the depth stop. I'm going to come down to 3/16 with a conventional drill, and then to counterbore the hole I've taken the same size drill, which is a 5/16 drill, and have ground the bottom surfaces flat with the necessary rake. So we're going with the standard drill and then go in afterwards with this to counterbore the holes. Slipped out the clamp. This isn't the only time that you're going to see work slip under a clamp. More on that later. So the countersunk hole needs to stop at 3/16. This is a piece of 3/16 sheet, so we need to adjust the depth stop to suit that. So here are the countersunk holes ready for deburring. Well, we're ready now to start fitting the gibs. So I need to clean up the top of the saddle. It had some old grease on there, so I'd use some solvent and just a little bit of wet and dry there to remove any surface rust. It's important that it's accurate here because this forms the base for the saddle to slide along, and also good location for the gib strips. So we're going to do some accurate measuring now, so cleanliness was necessary. Well, so far so good. It looks like holes are all lining up. Good. Now what I'm going to do is I'm going to remove this and set up this gib so that with a pin in the corner of the dovetail measuring off the faceplate, I know that this is parallel with the faceplate. Once I've done that, lock that down, I'm going to put this in, check for parallelism, get it parallel, and then I'm going to measure that dimension and check that against our drawing. Okay, I'll put this parallel up against the faceplate. So the clamp is there just to make sure it stays in place. Put a couple of pins of the same diameter against the right hand gib, and what I'm going to do is check that that dimension is the same. Now at the moment it's a little bit tight on this side as compared with that side, so I'm going to make some adjustments here until I get that perfectly parallel. Well, I very carefully measured this at both extremes, and the difference I get comparing the two with my 1 to 2 inch micrometer is 6 thou. So this is 6 thou tighter than this end. So what I'm going to do is I'm going to open up these two holes, the next size number drill, and I think that should give us enough clearance to rotate this sufficiently to get it square. So I'll just take that over to the drill those through, and then bring it back again. Okay, I've opened up the two outer holes, a whisker, and let's see if that gives us sufficient clearance to align it with the faceplate. Okay, I'm happy now that that is parallel with the faceplate. So I'm going to take the clamp off, remove the parallel, and we're going to put the other gib in and then try and get that parallel to the first one. And if we can do that, then we can take the measurement between them and check that against our drawing. Okay. Is a little fiddly. You can see I'm pushing the gib over to the left, taking up all the clearance to see if there's sufficient adjustment here. Okay, this end's a bit tighter. Okay, I'm going to open this hole up slightly so that we can bring this very slightly closer together. In fact, I might open these two up. No, I'm going to do the same thing. I'm going to open up the two M1s by the same amount I did on this side. Just very slightly, I'd say 1 or 2 thou tighter at this end as compared with that end, but it's worth getting it parallel. Eventually I got the desired result. It took quite a bit of fiddling around, certainly too tedious to show on a video. Eventually I will probably fit dowel pins to both gibs once I'm sure that everything is aligned and everything works properly. Okay, that's parallel. While we're measuring, I am also going to double check the position of the locating hole for the cross slide feed nut with this right hand gib. So I put the pin here, a gauge block and some feeler gauges, and getting a good measurement of this. So that's 18 thou plus the gauge block, which is 150 thou. So that gives us a setup like this. So 2 pins of 3/8 diameter, this pin of 3/8 diameter, and a gap here of 0.168. So I'm just going to transfer all this data to the CAD drawing, and we can correlate the actual measurements with what I planned. Cross-check the dimensions from the saddle and the gibs with the CAD drawing, and brought modified dimensions out to the workshop, and we are ready now to start to machine the cross slide, put the 2 dovetails in. So the setup took a little while to prepare. We've got a parallel here trammed in with the center line of the machine. We've got the work here which sits up against this, so we can machine one side, turn it over, and ensure parallelism of both the dovetails. I've double checked that the basic outline of this is square and parallel, so we can turn it over, and I think that will be fine. I've spent some time preparing the tool. It's got an appropriate profile so it can get right down to the bottom of the dovetail with the correct radius on the end. So what we need to do now is remove the work, put some marking layout blue on there, and mark out the outline of the dovetail, so we've got some lines to work up to. And as we approach the final dimensions, we'll use more accurate techniques to measure the dovetail. A quick update here using a sketch I showed in the last video of the cross section of the cross slide. You can see here the gibs and the general proportions. Well, I've just marked out the edges of the dovetail, and hope you can see that. So we've got a guide to work up to. We're setting it up, just taking care to ensure that the holding down bolts are as close as possible to the work, with the packing further away, as far away as possible. I think that all looks stable, and we're up firmly against the parallel, so we can tighten that home, and then we can take some roughing cuts and start to machine this dovetail. It was at this point I suddenly realised I regretted making good progress on this dovetail. The problem was it was the wrong angle. I'm so used to cutting angles like this from the horizontal rather than the vertical that I forgot to rotate the cross slide sufficiently. So I think that's an easy mistake to make. It's very easy to get 30 degrees and 60 degrees mixed up. Anyway, I was able to redeem the situation, as you'll see later. Not before I had another near disaster. Just coming up. Well, having had 2 clamping mishaps in the one video, I thought it was appropriate we have a closer look at clamping arrangements. So here you see a diagram of a machine table with a workpiece on it in red, a clamping arrangement, and a packing piece for the clamp. Now, if we look more closely at this, what we're really interested in is the force W to cause the work to slide on the table. And of course, that's going to depend on the clamping force through your holding down bolt. But not only that, the actual force on the work here, small f. And the other factor, of course, is the friction between the work and the table. And there is a coefficient, a number there, designated mu, which helps us actually work out what these forces are. And people have painstakingly worked out different coefficients of friction between different materials and tabulated them. So this effectively is a ratio of the force to cause the work to move as compared with the clamping down force. That's all it is. So the equation is W equals mu times F, and you can see that mu is going to normally be less than 1. So the force required to move the work is normally less than the clamping force. Now, for any material or combination of materials, there will in fact be two coefficients of friction. The first is the static coefficient of friction, and that is the friction which has to be overcome in order for an object to slide on another object. The other coefficient is the kinematic coefficient of friction, and that's the friction which has to be overcome to cause an object to continue to slide once it's already started to move. And some of you may be aware of the term stiction. It's this phenomenon that many of us experience in a workshop, where something sticks, and in order for it to move it needs a good shove or a knock with a hammer or a tap. But once it starts to move, it will move much more easily. So this is the difference between the two coefficients. So for cast iron, we can look up these two coefficients, the kinetic coefficient of friction and the static coefficient of friction. Now, I looked up the numbers for cast iron, and I was surprised to discover that the static coefficient of friction is actually greater than 1. It's sometimes as high as 1.1, which means it actually requires more force W than the clamping down force to get something to shift. But what wasn't a surprise is the kinematic coefficient of friction, which is as low as 0.15, and that is quite low. So if you put those numbers into our formula, then we can begin to make some calculations. But before we get there, we need to look at the geometry. So you can see here a clamp with length L, large L, and the distance between the fulcrum at the clamping end and the bolt is small l. And using that geometry, we can actually work out F and express everything in terms of large F. So we actually get this formula. It looks complicated, but it's not really. It just tells us that the force W is the coefficient of friction times big F, the force at the central bolt, ratio by small l over big L. Now, if we scale this drawing and put these numbers in, which I've done here, you find that W equals 0.5 times mu times F. Now, what I'm interested in here is the kinetic coefficient of friction, since that's the more conservative number. So if we put that in, we find that W is only 0.08 times F, or in round terms, W is less than a tenth of the holding down force on the bolt. And you can see immediately how a situation like this can become vulnerable. You think it's secure, but it's not that secure. If you want to improve things, of course, you can put the bolt up close to the work, and that's what you should normally do. And if you do that and actually key in the proportions that I have here in this diagram, the situation's improved. And now W equals 0.8 times mu times F. So again, we use the kinematic coefficient of friction, and we find that W now is better than 1/8 of F. So that's a considerable improvement. Now, what happens if you put the clamping down bolt at the wrong end? You put it up close to the packing piece. Well, again, using the actual geometry here and plugging that in, we find that W now is 0.3 times mu times F. And with the kinematic coefficient of friction, you can see that W is less than 1/20th of the holding down force of the bolt. And that really is going to be a very inadequate setup. So, what have I learned from this? Well, I think what I've learned is that I need to put more torque into that holding down bolt. Perhaps I've been cautious because I'm used to the rather weak T-slots in my Myford lathe, and didn't want to stress them too much, but on my shaping machine, I think I certainly need to tighten up these bolts more. Of course, this diagram shows the importance of positioning the central bolt, but it also tells you something about friction, and we need to consider different materials. I think cast iron on cast iron is a slippery combination. So there we are. I hope that you found something interesting in this. I think I've learned something. Well, this is what I've been able to redeem from the situation. There's a section from the middle there which is missing, but there's sufficient contact there for it to work. So I'm considering this a practice really. The real cross slide is going to be longer and to a new design, but I think it's still worth persevering with this. Well, that's all we have time for today. We've learned a little bit about clamping and the importance of ensuring that you have adequate clamping forces and correct placement of the clamps. We have almost completed the cross slide. It would definitely be completed in the next video because I've actually gone ahead and done the machining. It's just I didn't have enough space in this video to complete that. So hope you join me next time. Thank you for subscribing and giving me a thumbs up if you appreciate the video.